So, in previous lecture we talked about the strike slip fault, which we identified from close to Chandigarh area in northwest Himalaya. Now, coming to this, this is again a very well known location and the picnic spot also, you can say, or the tourist spot and hill stations. One is the Parmanu here, and then you go to Kasauli. Now, this is and even to Shimla from here. Okay, so this is in Kalka town, which is sitting in the Pinjore Doon area, and the fault which I was talking about, the Taksal fault, goes through here actually, this location. So, some close-up photographs and the points which we were talking in the last lecture, that if this fault was not known, then what the local people or the so-called urban development people did, okay, without having this information, because nowadays this is very much essential and slowly it is getting mandatory that any structure coming up in these seismic zones should have the report that whether that structure is coming on the active fault or not. So, fault trace is here between those two arrows, and if you see, this Parmanu is the town is very much close to the fault. Further, another close up of that. So, fault runs here, and I will just put the offset here of the stream which is flowing. Stream comes like that and then take turns here. Okay. So, let us see the close up of that again. Fault runs here, stream offset, and you can see at the backdrop a lot of construction which is close to the fault line. Further, ground photograph of that. Okay. Now, this photograph has been taken from this hilltop, okay, viewing this side. So, what you see here is the stream coming from here and taking turn that. Okay. So, this goes here. So, the fault runs somewhere over here. Okay, and this portion of the cliff or the escarpment is your fault scarp, and you can see that a lot of construction has been carried out on the top of this. Let us see close up of this area, where you can see the tank here. This is a water tank, and then few houses are sitting exactly on the top of the fault. Okay. So, this is a fault scarp on which this whole portion, okay, from here to this place is your fault scarp, and fault runs somewhere over here. So, now the point is whether this fault was known or not. The answer is yes, it was not known, and without having any understanding that in future earthquake what will happen. So, you can just compare or think what we saw in couple of previous slides from Kobe or Awaji Island, where the Kobe earthquake resulted into displacement. Now, this scarp which is seen here and more than 15 meters, okay, and in some places we observed that it is almost like 50 meters. Okay. This did not develop in one single earthquake. Okay. So, this itself indicates that there were multiple earthquakes which resulted into the formation of this high scarp. Okay. Again, this is not in very ideal condition to put a water tank on the top of the fault scarp. Second is this house which is sitting exactly on the top of the fault. So what will happen, that when the earthquake will come, this block will move as well as vertically, that is move laterally as well as it will uplift vertically. Okay. So both movement will be experienced here, and you can think over that what will be the ground acceleration in this area. Okay. So this area for sure will observe total damage. So this is one example which I wanted to show you, that what is the importance of delineating or identifying the fault lines from satellite photo interpretation. Another very good example from US. Now this fault is named as Denali fault. So what happened was that when they were putting, and this what you see here, the white line is the crude oil pipeline. So they wanted to lay the crude oil pipeline, so all the transects and the orientation, the alignment of the pipeline was decided, but they came across that, or they came to know that this pipeline will cross the fault line. So what is the best way to protect this pipeline from future earthquake? So they did the detailed studies on the Denali fault, that is what we call the paleoseismic studies, and they found that this fault will rupture in future. So the civil engineers and the structural engineers, they asked that, okay, what will be the displacement which is expected, and second is how much will be the amount of vertical movement in this area, okay, or along this fault, and what is the best way. Then they started, the thought process started was, and what is the best way to save this pipeline, okay, because whenever there will be an earthquake, this area will break, and then of course the damage will be experienced by the pipeline. So what they did was, they decided that fine, let us bring the pipeline on the surface rather than putting subsurface, okay. And since they knew that this fault is a strike slip fault, a right lateral strike slip fault, which will definitely will have an movement where the one block will move towards right and another towards left, okay, or maybe you can say that the block will move towards us. So they knew the sense of movement, and then what will be the offset, okay. And in later, so they put this pipeline on a slider beam, okay, or we can say very much similar to the roller coaster, okay, and they took into consideration the amount of displacement which one will experience along this fault. So they kept that much of buffer, that whenever they came up with a very flexible pipeline, and they put this on the wheels, okay. So when the earthquake came, this just pipeline slided on the top of it, okay, and did not damage, okay. And this is a very good example which we always talk about when we are talking about this one, okay. Now coming to the another type of fault, that is a normal fault, okay. So normal fault, what will happen, the hanging wall will move down, okay. whereas this wall, that is the foot wall, will remain stationary. So we need to also understand and identify that what is the type of faulting and how it will move. Okay. So normal faults, we have the foot wall, we have the hanging wall, and the foot wall block of the rock mass which does not move during the movement. Okay, it will remain stationary, whereas the hanging wall will move. Examples again from US, normal fault scarps, how it looks like in the field, and a fault line has been shown by the red line. The amount of displacement which will result into the formation of the fault scarps, and this is how it looks like. Okay, and this was by young displacement and really like 2 or 3 decades back. Okay. So normal fault after the earthquake, or for example the erosion, it takes place. This is an example from Bulgaria. So what you see here is that there is a ground here slowly getting elevated. Okay, so you have a very gentle slope which is coming up here. Okay. So fault runs somewhere here, and this is an example of a normal fault scarp. Okay, where this side is up, this is down. So in normal faults, what we were learning is that one block will move down, another will remain stationary. So this block has moved down. Okay, and this will be your hanging wall, and this will be your foot wall. So here this is your hanging wall, sorry, this is your foot wall. So this is your foot wall which is stationary, and this is your hanging wall which moved. Another photograph of same area. So for this, what they did was, the best way is to identify the displacement, how many earthquakes took place on this fault. So they open a section, because that's what we were looking at when we were talking about the folds, when we were talking about the faults, that we should see the section. For example, if we have a block movement, okay, so on the surface you will be able to see this scarp. Okay, but in section you will be able to see the net displacements. So this is your surface. So to see this part here, they opened up a trench somewhere at the base of the scarp, and this is what has been shown here. Okay, fine. And this is what they got. Okay, so this is a scarp here, this is a foot wall, and this side is the hanging wall. Fault runs somewhere here. Okay. Another close up of that. So you have an fault trace. So this block moved down along this fault here. Now what we see here is very quickly I'll just explain that why we say that this will move in future. Okay. And there are chances of this fault to move in future. Now what will happen is, this is a present day ground surface here. So when the next earthquake will come, this will rupture. So this will move further down, and this remains stationary here. So to avoid this, we need to identify the topographic expressions of such deformation. So fall block, mountain range produced by normal. Okay. So this is in combination, usually in seen on the larger scale. If you look at, we will find something like this. Now topography, if you see, will be slightly similar to the topography which you will find in folded mountain chains. Okay. But here what we consider that the host is a stationary one, whereas this blocks will move down. Okay. So normal faulting usually you will find the combination of host and graben. So topography you will see something like that. So host, a block, because if you take in a strict sense, then you find that this block has moved up, okay, with respect to the graben here, okay, or the block which is sitting adjacent to it. So the block of rock thrown up between the two normal blocks. Okay. Graben is termed as a block which is thrown down between the two normal faults. Now most of the geologists believe that host structures are formed by compression, as two reverse faults are thrusted up, whereas some believe that host and graben pair can occur in an area of rifting or in extensional environment, okay, where the crust of the earth is being pulled apart and normal faults are formed. Okay. So this is in the extensional tectonic environment. Okay. So if you look at this, what has been shown here, that this level has remained as it is, whereas this block moved down. So if you stretch something, what will have, you will have the breaking and the blocks moving down, and that is your combination of host and graben structure. So this cartoon explains that you are stretching the plate or the crust, and the block in the center along two normal faults is moving down. Okay. So this is your foot wall, this is also your foot wall, and this is your hanging wall. And in terms of the structure, this will form your host, this is also your host, and this is your graben. So from aerial view or from the satellite data, how it looks like, okay, you will have a very linear ridges and associated valleys. Okay. So extension. Now coming to the reverse fault. So as we were talking about that in strike slip fault, one block will move towards us or away from us along the strike, and in combination you will have the movement taking place up along the dip. So here it is reverse what we see in the normal fault. Okay. So this is your hanging wall and this is your foot wall. So this block has moved up along the fault plane. So reverse fault, hanging wall, foot wall, and this we have already discussed, so I'll just move ahead. But this is important, that when we are talking about the reverse faulting, then what we see is that we have the shortening of the earth crust. Okay. But when we are having extension, then we are stretching the earth surface. Okay. This is an example of the thrust fault, where this is a footwall and the overriding rock block is folded. So thrust goes here, because thrust we will classify as an low angle reverse fault, and we see the folding taking place over here. Okay. So this you will be able to see in the section, whereas on the footwall side you see all statas are horizontal. Now this is the part, again coming back to India, close to the Chandigarh area. So what we see here is, in this we prepared using SRTM data and using the software NV, which you will also learn in some of the labs. Okay. So we see a very clear-cut topography which has been marked by different colors here, and this region, what you see here, is your lesser Himalayas, and this portion is your inter-mountain valley between the two ranges. Okay, and this is your youngest mountain chain, which we say sub-Himalaya or Shivaliks. So the contact here, as we were talking about, this is the contact which is marked by Himalayan frontal thrust. So this side is your Indo-Gangetic plain, and from here you start having the Himalayas. Okay. So this one is another example of the Taxal fault. I'll just check whether we have the video of this so that we can play for you. Let me remove this. Yeah, you can see this. So this part also you can do on NV. You can fly through the terrain and then look at the different examples. Okay. So here, which you see is your Taxal fault. Another close-up of that Taxal fault here, where we can see a very straight valley and then offset of streams also, and another fault which is lying here. This is your Barsar thrust close to the Pinjore Dun, and how it looks like when you look at the 3D. Okay. So now you can clearly see this line coming here. Okay. This is your Taxal fault, which is a right lateral fault, and here is the Barsar thrust. So what we basically found here was that in this area, in a very short distance, we looked at 1, 2, 3 and 4 faults. Okay. And all four faults are active faults. Okay. So this is extremely important for us to understand. So if you look at these 4 faults, then what is the history on this? Until now we have identified that this fault ruptured or triggered the earthquake in 1500 AD. Okay. And Pinjore fault or Pinjore Garden fault, I will come to that. Then another interesting story here. Okay, it triggered the earthquake, 2 earthquakes in last 10,000 years. Okay, one was around 4,000 years and one around 10,000 years. Still we have been trying to identify on what happened on Taxal fault and Barsar fault, but recent studies, which is still under we are preparing the research article, there was an earthquake in 1400 AD on this actually. So coming to this part, that we can prepare a very detailed map after doing a proper interpretation. Let's see some more information on the fault lines close to Chandigarh area. Now before going to that, let me just quickly explain you that what exactly you see here. Okay, well, this is again corona satellite photograph, high resolution, and we have tried to merge two photographs over here. So this line is not a fault line, but this is just an merging of two photographs. You can see the construction pattern here, well planned city of Chandigarh, and this is one fault line here which you can identify, that is the contact, geomorphic contact between the hilly terrain and the flat areas. Okay, another contact, very sharp contact, is here. Okay, this is again in flat area which is in Pinjore Dune or Pinjore Valley, and further getting into the lesser Himalayas here. Okay, this is the same map which you are seeing on the right is a colored map of, that is geomorphic map, which I was showing earlier. So you can compare the photograph on the left and the geomorphic map along with the surfaces as well as the fault lines to understand that how we have extracted the information using the satellite data and prepared our fault map or morphotectonic map of that particular region. Okay, I'll continue this in greater detail in the next lecture. Until then, bye and see you in the next lecture. Thank you so much.